Thank you for inviting me to give this colloquium to the computer science program. I apologize. I just realized that while I was like reshuffling slides, I forgot to update my first slide with my affiliation. I am now at Boise State, no longer at the University of North Texas. I'm in the chemistry department right now. I used to be in the physics department. My research is in computational science. I would say that my research encompasses physics, chemistry, and material science. Like several groups involved in computational science, we focus on 3 different activities. We develop models, and I'll explain later on what these models, the models that we develop are about. We implement these models into codes, and we try to make them faster. And all the software that we develop is open source. And then we use these models and this software to simulate specific applications. And I'll be probably very quick or on the application side, because I'm assuming that you guys would be more interested in the first 2 part of our research activity. And in fact, the first 2 points are the ones where I personally like to spend most of my time. And again, I apologize for the QFT logo here. Now I'm at Boise State in the chemistry department, but this website should be updated, and you should see all the relevant information on my group and research over there. How we do this, especially the first 2 things, I like to organize hackathons to put together people that develop similar tools or that work around the same kind of software, and get together in a very informal environment. And especially, I found this very useful for young researchers and students to get started with their projects and to see how other people work and to interact directly with other developers. And we organize tutorials and schools regularly. We had a school on multiscale models in condensed matter and materials simulations, and the recordings of the school are all available online. So I encourage you, if any of the topics of this presentation are of interest, you can go there and look at the videos of where we go a bit more in depth in some of the models that we develop. So simulations for materials design and for chemistry traditionally started as a support for the experiments. Right? You have some scientific problem that you want to solve, or you want to identify a class of materials or a class of chemical compounds that work well for a specific problem. You do the experiments, you measure the properties of your system, and then you would like to have some backup from theory. And nowadays, there is very little you can do with pen and paper theory. So most of the theory, or let's say most of the validation of the experiments come from simulations. And so you'd like to ask your computational colleague to try to run simulations on your experiments and validate the simulation. The advantage is that the simulation can provide way more details and have way more control on some aspects than the experiments, which means that if everything goes right, the simulation can actually guide further experiments or like suggest ways to improve some materials or some compounds. However, as computational scientists or scientists in general, we should not just aim to be of support to someone. We would really like to be the first to get somewhere. And so nowadays, especially in materials, but this has started in chemistry before, we can move to a different paradigm where simulations are really the first step when you try to design a new material or you try to design a new drug. You basically study systematically everything, and then you extract patterns and understanding and design principles from your simulations, and these are used as the first step to guide the experiments, say to guide the synthesis of a new material. And if you want an example, in drug design, when people identify a protein that is responsible for a specific disease, and you try to target the active side of the protein, the first step is usually a systematic screening on the computer of all possible organic molecules to see if they fit in the active pocket of the protein. And so this docking-like problem so computational screening is really one of the first steps in design nowadays. And one of the advantages being computational scientists is clearly that our experimental equipment gets better and better without us doing anything. So you probably all know this, working in computer science, but clearly the fact that computers become more powerful per se is not enough, because there are a lot of properties of materials that are still beyond reach of standard computer power. And so we need to develop a better algorithm, and we need to develop better methods to tackle very complicated systems. I want to give you one example where this approach to materials design has been very successful in the recent past. You may have, I know that the audience comes from all different backgrounds, but you may have heard about graphene. Graphene is the first known two-dimensional material. It's a material made of just one layer of atoms. So it's one atom thick in one direction, and then is macroscopic in the other two directions. It was isolated in 2004 by peeling one layer from graphite, which is a bulk material. And it got Nobel Prize in 2010. So it was one of the fastest Nobel Prizes in the recent history. And since the discovery of graphene, there has been a few tens of 2D materials that have been realized, and some of these have been realized in a similar way to graphene. So the idea is we could take a bulk system that we know is layered, and we can peel one layer off. Or some of these, like boron nitride, is really just a graphene where we replace two carbon atoms with the nitrogen and the boron, and nitrogen and boron are at the two sides in the periodic table with respect to carbon. So in terms of the electronic structure, this system is isoelectronic with graphene, right? So it's basically just doing an alchemical transformation of carbon atoms into nitrogen and boron. However, with computations, we can systematically try to figure out if we can synthesize other, we can try to figure out if other possible 2D materials exist. And these are two different works in this field, and there are more, and there have been more and more in the recent past. So 2D materials have been a very active topic of research. The idea here, especially the one on the left of this work on the left, was can we look at databases of crystal structures, so bulk materials for which we have the known crystal structure. And you would think there are billions or trillions of crystal structures that are known to mankind. But as a matter of fact, if you take all the databases of crystal structures, we have about 200,000 unique structures. So we're not speaking about trillions of crystals, right? And so what this group did was very smart, was can we look at the topology of these crystals, just looking at the connectivity between the atoms in the crystal cell, and try to figure out if the topology corresponds to systems that are layered. Right? If the bonds between atoms or the atoms are close together in two directions, but farther away in the third direction, then these crystals are really layered systems, right? And by doing that, they figured out that out of these 200,000 structures, about 5,000, only 5,600 are layered structures. And then they could do simulations to figure out what is the strength of the interlayer bonding. And they basically divided these 5,000 structures into high binding energy, potentially exfoliable, and then easily exfoliable structures. And the black dots correspond to the 2D materials that had already been isolated experimentally. But the cool thing is that with this kind of study, which was really starting from like a very simple idea, they could actually figure out that about 1,800 structures would be potentially exfoliable. And so far, only a few tens have been realized experimentally. So this really gives a different perspective on how computational science can provide insights that can be used by experiments. And so this is, if you want, this is the peeling idea. How many bulk structure can be peeled off? And in this idea here, instead, is a more of an alchemical transformation idea. The idea is, can we take some prototype structures of these 2D materials, because we know that some of these 2D materials have already been synthesized, and can we substitute elements in this structure and see if they are stable? And so here again, this is another big database of computationally predicted 2D materials. And this idea of high throughput simulations for materials really started in 2011 with the Materials Genome Initiative, which was brought forward by the Obama administration. And the idea of this initiative was really to accelerate the time to market for new materials. And one of the key aspects was the computational design or computational tools to help design materials. So what do we need to go high throughput? What do we need to be able to predict new materials in a high throughput fashion? So one key aspect that has been developed in the past years is a computational infrastructure. So we need a way to submit thousands, hundreds of thousands of simulations in an automated way and retrieve the simulation results, save in a structured database all the input and output, and then be able to do queries on your output. But then we need a simulation method that is somehow accurate for all the different possible materials in a qualitative sense. So we want it to be transferable between different materials, and we want it to be fast enough that we can simulate hundreds of thousands of materials in a matter of days or weeks, not years. In general, the key technique that is used for this purpose is density functional theory, which is a way to simulate or to compute the electronic structure of the materials. And this leads me to the next slide. I'm not sure how expert you guys are with simulation techniques in materials and chemistry. And so I thought I'd put together a sort of an overview of the different kind of techniques that exist in computational physics, chemistry, materials, with the timeline of the theories that are behind it somehow. So clearly, when we look at matter as made of atoms and so ions and electrons, ideally we would like to use quantum mechanics. We know that at least electrons are typical quantum mechanical particles. If we look at ions and electrons, then the only interaction between these things is electrostatics. So we don't need any empirical description of interaction between particles. We have clear electrostatic forces. The problem is that we need to solve for the wave function, the many-body wave function of all the electrons in the system. And traditionally, there have been two lines of developments in this field. One has been brought forward more by the chemistry community. And so what I call QC stands for quantum chemistry. And quantum chemistry really developed a set of tools that are ideal for isolated molecules. So a collection of a few number of atoms with their electrons in vacuum. In the meantime, physicists started looking at a periodic structures because we wanted to characterize like electron gases, metals, semiconductors. And it turned out that in this field, it's actually convenient to, instead of solving for the many body wave function of the system, you can recast the problem in terms of an energy functional, energy as a functional of the electronic density alone. So the cool thing there is that you only need to solve for a function, the electronic density, which is a function of 3 variables, so function of space, instead of having to solve for a wave function that is a function of the coordinates of all the electrons in the system. The tricky part is that although there is so density functional theory in principle is exact, there is no analytical expression for the exact energy functional. And so there are a bunch of approximations that have been introduced over the years for energy functionals. And in the 80s, actually in the 90s, density functional theory met quantum chemistry and gave birth to what are known as hybrid functionals, which have since then become very popular in quantum chemistry as well. And they are pretty accurate and are probably the de facto standard nowadays to simulate organic molecules. Hybrid functionals are less popular in condensed matter in physics. The issue is that if we focus on studying a matter with the electrons in it, so if we want to do quantum mechanics, then our simulation scales as the number of electrons to the cube power in the best case scenario, if we are not doing fancy quantum chemistry methods or other things. And so you can see that this becomes easily intractable, and usually we can only study systems with about a few tens of atoms, maybe 100 or 200 electrons, or up to in a matter of hours or minutes, but then we can do 100 or 200 atoms in a matter of days. So here we are already far from what we would like for high throughput simulations. So this is clearly an issue when you are studying disordered systems like liquids or amorphous, because disordered systems require to have large simulation cells, because otherwise if you have a small simulation cell and you repeat it over and over, then it's not disordered anymore, because if you have 10 atoms in a cell and then it's periodically repeated everywhere, then you can't really say that it's a disordered system. And so you can easily see why liquids have been very difficult to study with quantum mechanics. And the second reason why liquids or statistical systems are challenging is because of what is known as a timescale bottleneck. The problem is that not only we have to simulate a large system, but we have to simulate different realizations of a large system, because it's a statistical system. So a single configuration is not representative of the physics of the system. So you can't just take one snapshot of liquid water and pretend that this describes the physics of liquid water. You need to usually study thousands of snapshots. And so traditionally, statistical simulations of matter have relied on classical descriptions of matter. And by the way, statistical simulation like Metropolis Monte Carlo or classical molecular dynamics really are among the first computational science applications that have run on a supercomputer. So traditionally, high throughput DFT simulation focus on bulk crystals, slabs in vacuum, or isolated molecules. However, there are a lot of properties of materials that instead would require to simulate wet, possibly electrified interfaces. So one typical application is very popular nowadays, is related to energy and fuel conversion. Like can we study some of these devices that convert electrical energy into fuels, or vice versa, fuels into electrical energy, or store electrical energy in one way. All of these devices somehow feature condensed matter, a solid substrate in contact with a statistical, like an electrolyte solution, a liquid, and possibly in the presence of an applied potential. And so there are a lot of problems, a lot of technologically important problems like corrosion or stability of materials, like battery materials, that would require to simulate interfaces in the presence of a liquid solution on top. And as I just said, that is very difficult to do that with full ab initio with like quantum mechanics. There are some groups that do quantum mechanical simulations, so there are like some groups that develop code that scale up to like thousands of cores, and you can run big simulations. But the problem is that even if you can do one simulation for a very big and complex system like the one on the left, I mean, you can't do this in a high throughput fashion. And so you can't really use this kind of strategy for a systematic screening of materials. And so there are different levels of theory. You can somehow simplify the description of your statistical system. Maybe you can treat the water molecules as classical objects. You have to parameterize an interaction potential between different water molecules. You can use coarse-grained models. What I'm going to talk about today mostly is the use of continuum models. The idea is that you need to take the statistical average of the effect of the liquid on your substrate. You may as well replace the liquid with its statistical average, which is you can get rid of the atomistic details of the liquid and treat the liquid part of your simulation as a continuum, homogeneous continuum body. And this is justified if you take the full quantum mechanical simulation over time and you look at the average density of water molecules in the space above your substrate. You can see that on average, the water molecules are everywhere in a continuous fashion. And there are some spots where the water molecules sit a bit longer or a bit less long. But apart from these spots right at the surface, a continuum description of the liquid system seems to be, in the statistical sense, seems to be a reasonable approximation. And this has been a collective effort in recent years. So I would say it really started in around 2002, 2003 with the work of Fateber and Gigi. Let me clarify one thing. These continuum models of solvations have been around for a very long time in quantum chemistry. I told you at the beginning that quantum chemistry simulations focus on small molecules in vacuum, but most of chemistry happens in solution. And so continuum models have been introduced in quantum chemistry a long time ago, and they've been quite successful, but they've been not used in material simulations for a while. And I'll try to explain the reason why there is a difference between the two in a second. But the idea is that from the year 2000, many people realized that we could use these models in material science. And nowadays, every simulation package in materials and condensed matter physics has a module or has the capabilities to include these continuum models of solvation. And so these are the three main developments that are pursued in my lab. The first one, Environ, is probably the most mature one. This is a library that develops these continuum models and is coupled with mostly with the Quantum Espresso, which is a simulation software in condensed matter physics. Is an open source software. It's probably the most widespread open source software in condensed matter physics and materials. The most widespread software is called VASP, but it's a commercial one. And many people use VASP because it's faster. On the other hand, Quantum Espresso is less of a black box. So if you do things wrong, Quantum Espresso will not converge. And so you know that you have done something wrong. We are also refactoring Environ in Python, and I'll explain a bit more what this means. In a second, is one of the new directions in my lab. And we're also developing workflows and plugins to automatically do more automatic simulations of like high-throughput simulations. So a bit more on continuum models of solvation. There are two main ingredients in continuum models of solvation. And let me clarify one thing. In continuum models, the idea is that we have part of our system, which we call the well, we call it the system or the solute because we are looking at something in solution. So we, in chemistry, especially, we call this as the solute. In this case, we could call it the substrate. So this part of the system is still treated with the highest level of accuracy, because what we want is to predict properties of the solute. We want to predict the catalytic activity of a certain catalyst material. We want to predict the stability of an interface of a material. And so this part of the system is treated with quantum mechanics, density functional theory, or so we are trying to solve the electronic structure of the substrate of the solute, okay? But we are trying to do it by immersing it in a continuum medium. And so we need to define two things about this continuum medium. We need to define the shape of this continuum medium, or if you want, we need to define the interface boundary between what is quantum mechanical and what is a continuum. And then we need to define how the quantum mechanical system interacts with the continuum. So we need to have a recipe for the interaction between the quantum mechanical and the continuum. In terms of the interfaces, we could think of very geometrical interfaces. So the very first continuum model is probably the Onsager model for solvation, which was just a spherical cavity in a dielectric. This is a typical problem that you solve in electrostatics, so it's in the Jackson textbook kind of problem. But it was soon realized that if you take very geometrical interfaces, they may be easy to solve analytically, but then they're not really realistic in terms of their results. And so eventually people realize that you need an interface that mimic the shape of the solute. And traditionally in quantum chemistry, this has been done by placing a sphere on each atom of the solute. But more recently, people realize that we can also use the electronic density of the solute to determine the shape of the interface. Because where the electronic density is low, then that's where the continuum will be. And where the electronic density is high, that's where the quantum mechanical system is. And so there are advantages in both approaches. Bottom line, they both work the same in terms of accuracy if you parameterize them well. And then you have to choose what kind of interactions to turn on between the continuum and the quantum mechanical system. So usually solvent effects are electrostatic in nature, especially if you look at something like water. The effect that water has, so water has a permanent dipole because you have an oxygen and two hydrogens. The oxygen is slightly negative, the hydrogens are slightly positive. So you have a permanent electric dipole in water molecules. What these dipoles do when you have a solute, they'll try to orient themselves so that the electrostatics of the solute the electrostatic energy of the solute is lowered. So if you have, say, a positive charged solute, the waters will reorient with the oxygens, which are negative, and vice versa if you have a negative solute. And so in general, the electrostatic interaction between the solute and the solvent is one of the strongest components of the effect of the liquid. But there are many other kind of interactions. Some of them are more quantum mechanical in nature, and some of them are more statistical in nature. Like you need to spend energy to create a cavity in the liquid that hosts the solute and things like that. So the key component of most continuum models is this dielectric screening effect. And so the idea is that we can model the effect of solvent degrees of freedom, both the ionic one, so the effect that the dipoles will reorient, and the electronic polarization in terms of the static dielectric permittivity of the medium. And assuming that we have an interface function, where I didn't introduce it, sorry. If S of R describes is a function that is 1 inside the solute and 0 outside, we can define a dielectric permittivity in space in terms of this continuum interface function. And then we can introduce an electrostatic energy functional, that now includes electrostatic interaction between charges, as well as the total electrostatic energy, the polarization energy induced in the dielectric. And if we use a variational approach, we can figure out what the electrostatic potential is in the presence of the dielectric. Basically, we end up with a differential equation that is known as a generalized Poisson equation. The Poisson equation in vacuum would be the Laplacian of phi is minus 4 pi the charge. In this case, since we have a dielectric medium, we have this extra term here. And so numerically speaking, I see there is a question in the chat.
Oh, no. So I'll pass if there is a question.
Yeah, sure. Numerically speaking, this is one of the numerical problems that these continuum models have to solve. Traditionally, if you do a quantum mechanical simulation in vacuum, you only have to solve the Poisson equation in vacuum, which, I mean, there are a bunch of techniques that you can use. If you have a periodic system, the easiest one is just to use fast Fourier transforms and solve the Poisson equation in reciprocal space. If you have a system, well, I mean, for quantum chemistry simulations where you don't have periodicity, they have different ways of solving the Poisson equation in vacuum. If you want to have a problem in a continuum dielectric medium, you have to solve this problem, which is a bit more challenging than just Poisson equation in vacuum. And so the first people that proposed this, they relied on a multigrid solver to solve the Poisson equation in a dielectric. What I did when I started playing with the initial implementation was that I mean, at the time we had a multi-grid solver that was not parallel and required a different grid from the FFT grid of the condensed matter code. And so there was an interpolation step. I found, and the calculations were not converging, so I found it was a bit flimsy as implementation. And so I basically recast the solution of the generalized Poisson problem in a way that only still relied on FFTs for the Poisson problem in vacuum. And then I did a sort of a fixed point iteration on polarization charge. And in doing that, I basically realized a better way of defining the interface function as a function of the electronic density. I don't want to go too much into the details. If you have more questions about this, I'm happy to answer these questions. And then later on, we realized that we can use something a bit better, which is basically using a preconditioned conjugate gradient algorithm, where each step is still based on FFTs for solving the Poisson problem in vacuum. And here there is one aspect which is a bit more technical, a bit more numerical, but I thought maybe in a computer science program it's relevant to speak about this. So basically, continuum models in quantum chemistry, which I said has been around for a while, they only rely on definition of the interface which are sharp. So they basically have spheres on each atom, and these spheres have, I mean, basically inside the sphere you have vacuum, outside the sphere you have a homogeneous dielectric. And what they did was they discretized the surface of the spheres, so they use a boundary element method to solve for the electrostatic interaction between the solute and the solvent. And they did that because traditionally in quantum chemistry, the electronic structure problem relies on a basis set which is localized on the atoms. And so the numerical domain of the quantum mechanical calculation was all localized on the atoms, and there was no numerical domain in the environment side. And so they had to introduce a new numerical domain just to describe the interaction with the solvent. However, in condensed matter simulations, we rely on a structured grid, which is everywhere in the simulation cell. So we basically have a numerical domain for the electrostatics or for the quantum mechanical problem, which is homogeneous everywhere in the simulation cell. And so the idea that Fatber and Gigi had is that we can rely on the same grid also to study the problem in the dielectric. But in this case, we need a dielectric, an interface function which is smooth, because we need to be able to map it in this structured grid. So we can't deal with a sharp interface, because that would not map on the grid points of the simulation cell. And so in a way, the approach in condensed matter physics is less ideal, because the problem now it becomes a three-dimensional problem and no longer a two-dimensional problem. So the dimensionality of the problem changes, but on the other hand, we can use things that were really not working well when you had a sharp 2D domain. So I spoke about electrostatics, this dielectric interaction. We have some more empirical ways of handling other non-electrostatic interaction with the solvent. It's not really relevant to see, to describe what these are. The point is that these continuum models do a reasonably good job in predicting solvation free energies for organic molecules in water, for example. And they do pretty well with many kind of organic molecules, but they do not so well with some specific type of organic molecules, in particular bases and acids. And so chemical accuracy is 1 kilocalorie per mole. On average, the error for these 240 molecules is 1.2 kilocalorie per mole. So we are a bit above chemical accuracy. On the other hand, the molecules that are above chemical accuracy are all molecules that are known to have strong interactions with the solvent. And so somehow replacing the solvent with a continuum for some of these molecules must be a crude approximation. And so, as a matter of fact, I think it's reassuring that our continuum simulations don't capture well the solvation energies of these groups in red, because they are known to have stronger solute-solvent interactions. So how do we solve that? In principle, we can include some explicit solvent molecules in the simulation when we know that these are important. So when you have an electrified interface, the use of just a dielectric medium is not enough, because you want to have an applied electrostatic potential. And in order to have an applied potential, you need to have a conductor, something that conducts electricity in the solution side of the simulation. And so you need to really include a description of the electrolyte. If you want in electrochemical field, we speak about a diffuse layer or a double layer. We need some ions on the other side of the electrode, so that overall the simulation is charge neutral. This requires to introduce, to make the problem even more complicated, and to introduce a continuum description of the electrolyte, which now is the solution of a Poisson-Boltzmann equation. And the problem with this continuum model is that now the electrolyte distribution depends exponentially on the electrostatic potential. And so this is a problem that is really not well conditioned. Especially if you are looking at a flat interface. It's a bit better if you're looking at an isolated system, like a zero-dimensional system. But for 2D, the potential, in principle, a charged surface generates an infinite, like a linear varying potential, an infinite energy system. So it's a bit of a mess. So what we did was, at the beginning, we started implementing simpler models. We implemented some analytic solutions, some linearized Poisson-Boltzmann problems. And then eventually we figured out a Newton-like algorithm that converged for this Poisson-Boltzmann problem. And we got results that are sort of encouraging, because we can sort of reproduce the shape, for example, of the differential capacitance of silver in solution. We can, with our model, we can sort of reproduce the right behavior. Although, it's difficult to know if we include all the ingredients or everything that happens on these electrified interfaces in our continuum models. So I think I need to skip some of the slides because what time, like
So
5
we
minutes?
have about 18 minutes left.
18? Okay, then I have plenty of time. No, but I want to leave some time for questions.
Yeah.
So one other, I know there are a lot of technical details in this, but I'm trying to target this presentation towards more of the geometrical or mathematical problems rather than the applications. And so one of the problems that we have with these continuum models and that have been around, for example, in the quantum in the chemistry community for a long while, and I believe we found a smart way of solving it, and the smart way is only possible if you have a smooth interface continuum. So again, even though we are losing the two-dimensional nature of the interface, by going in 3D, we have some advantages at the end. Is the problem that when you start having complicated solutes with many molecules, then you start having issues because you have some voids in between molecules, and these voids, I mean, there are no degrees of freedom of your solute in these voids, and so a local algorithm, a local definition of the interface will just fill those voids with a continuum, right? So if you say you put a sphere on each atom of your system, and then here there are no atoms, the algorithm will understand here I have to put the continuum. But sometimes this is wrong because a solvent molecule will not be able to penetrate here. Okay, so the continuum region should really be defined on where the atoms of the solvent can access. On the other hand, the only way we can define the continuum region is in terms of the degrees of freedom of the solute, because those are the only ones that we have access to. And so we have an issue that sometimes there are regions that you don't want the solvent to penetrate, but I mean, a local definition of the interface will not be able to describe that. So how do we correct for this? Basically, we use a convolution with a spherical probe to figure out, I mean, say that we are sitting in these regions that is void, so there is no, there are no degrees of freedom of the system, but we know that this region is surrounded by degrees of freedom of the system. So in this surrounding area, it's all quantum mechanical stuff. If we take a convolution with a sphere that is twice as big as the solvent, and we measure how much of this sphere is occupied by quantum mechanical stuff and how much is empty, we can have a measure of, we can actually correct, we can have a correction that fills up vacuum regions that are inside the continuum regions. And the cool thing about this definition is that it's a continuous smooth definition, so we can take the derivative of this with respect to the degrees of freedom of the solute. And this is important because we need to compute forces and we need to compute these derivatives for the optimization algorithm. And so, and in this picture, everything is differentiable. And it doesn't require any user input. This is all defined in terms of geometry and the single parameter that is the parameter here that you can see is field fraction. So the idea is how much of this sphere is filled. If you send the field fraction to 0.7, you basically exclude all these bubbles or like spurious regions of continuum from your simulation. And this allows us for the first time to do simulations where we have a substrate and then some layers of water molecules. Before, the simulation would not converge. And the problem was that the continuum would penetrate in some of these regions, and these regions of continuum would be very small, and so numerically it would not be very well conditioned. I mean, it would not be, would not converge fine enough. But now what we did was, can we look at, so we have on one end, full atomistic simulations with molecular dynamics, so statistical description of the liquid for a bunch of different surfaces of semiconductors. And then we try to look at what if we replace some of the water molecules with a continuum? Will the simulations converge at a certain point? And what we realize is that although the fully continuum simulations are not perfect, we only need one layer of water molecules described explicitly, and this is enough to get to the same kind of simulations, to the same kind of result as with the full water molecules. And so this is nice because clearly we reduce a lot the number of electrons and the requirement for the statistical sampling of configurations. And so this, I think it's very promising. We have this skip. So I will not go over all the details of what we've done, but the idea is that now that we have these models, we can actually study materials in wet electrified environments. And so we started looking at 2D materials because again, there is a big, there are many databases of potential 2D materials. And so these are computational databases. So some of these materials have not been realized experimentally. So what we thought was, can we predict the catalytic activity of these materials so that maybe someone can try to synthesize the ones that we find more promising? And we started by looking at the hydrogen evolution reaction, HER, basically the process of taking water and converting it to hydrogen. This is not one of the most technologically difficult steps, but still it would be interesting to see if we can find materials like some of these 2D materials that do a good job. And we did a systematic screening. We started from about 200 materials. We did simulations in vacuum as the first step because those are cheaper. And then we did simulations in our continuum environments to compute the catalytic activity for in this case, hydrogen evolution is a simple process that only requires one exchange of electron. And so the H plus electroabsorption is really the limiting step. So we characterized that, and then we studied which materials were conductive, and then we studied which one of them were stable in aqueous environments, and we ended up with a list of 15 possible materials, and this would be the top 2. I don't think you're really interested in knowing the physics of these materials. And then we moved forward to a more challenging problem, which is the oxygen evolution reaction. So if you want to think about water splitting, the hydrogen is one side, the oxygen is the other side. And the problem with the oxygen evolution is that now this reaction requires 4 steps. And we have a recipe to put together these different calculations of these different steps into a single catalytic activity measure for the material. And the problem is that, and so we did this simulation for the transition metal dechalcogenides, and again, we figured out about 20 materials that seem to be working well for this kind of problem. But the problem is that in this study, we only focused on a single site pathway. But in principle, these catalytic reactions, especially when they involve multiple electron transfer, they can go over many different kind of pathways. So you can have absorption on one atom and then another absorption on a different atom, and then the atoms react together. So in principle, the number of simulations that you have to perform to have a very accurate description of these catalytic reactions grow very easily with the complexity of your system. So in this case, we did simulations on a material's edge, which again is a bit less symmetric than the material, let's say, basal plane. And we had to perform many different calculations just to figure out one pathway that was compatible with the experiment. As a matter of fact, we found 2 different pathways that had very low overpotentials, which was found in the experiments. And so the idea is that we have the more complicated our subset become, especially if we want to study defects that are usually catalytically more active, the larger the number of simulations that we have to perform. So in the last couple of slides, and then I'm done, I'd like to show you some of the directions where we are currently working on. So ideally, we would like to improve the accuracy. You have seen these error bars. We've seen that some molecules and some materials are not as accurate as others. So we'd like to improve on that in a way that is not just empirical, it's not just adding more parameters. We would like to improve on the transferability and extend these models to systems without the need for more empirical fitting. But we would also like to speed up our simulation and do more applications. And so one of the projects where I'm working on is, as a matter of fact, related to the fact that we can do hybrid simulations. And so we are refactoring our Fortran-based module in Python. And this is going together with other refactoring or let's say other Python interfaces of existing multiscale approaches. Because the idea is to combine together a subsystem DFT, which is a way of splitting a big quantum mechanical simulation into smaller simulations, with classical polarizable atomistic models, with our continuum models, with possibly other multiscale models. And the idea is to do this in Python because it allows more flexibility in developing these multiscale combinations. And the challenges are that, especially if we start looking at very large simulations, then the cost of an environment calculation, so the cost of solving this generalized Poisson equation starts to become the limiting factor. So for a quantum mechanical simulation, environment is not very expensive. But if you start to have a very large system where maybe most of the system is treated classically, then the environment part of the calculation starts to become really expensive. And so we are experimenting with using different ways of solving generalized Poisson equations. I mean, possibly we can use multi-grid solvers if they scale well and they are parallelized, or we can use other solvers. We can get a better way of to find the initial guess for the solution, or a better preconditioner. So these are all things that are more in line with the computer science, computational science kind of research. We need to find a way to couple the continuum and point-like polarizability in a single framework. I have some ideas on this. This is more of an electrostatic kind of problem. And then we need to develop tools that simplify the user perspective. When you start to have all different methods that interact together, it's difficult to set up the right combination, right? And so I've seen this in machine learning. One of the main advantages of machine learning software like scikit-learn or TensorFlow is not the fact that they implement a lot of different methods, but is the fact that they allow you to test them systematically in a very easy way. And so we would like to develop something similar for our multiscale combination of stuff. And we would like to also improve solvation using a more bottom-up approach. And so can we make a continuum solvation a bit less empirical? Or better, can we capture the deviation from an ideal continuum using full atomistic benchmarks? And this is more related to, say, machine learning or regression, like more accurate simulations into simulations that have less degrees of freedom. So we have introduced a set of descriptors that are atomic, that depends on how close each atom is to the environment. We need some symmetries to be preserved. So we need to be these descriptors to be rotational invariant, translational invariant, permutational invariant. And so one idea we had is we can use the interface function that we have in environ to define atomic descriptors by measuring, for example, how much of the volume of this interface function or how much of the surface of this interface function is within a certain radius from an atom. So we have this kind of curves for each atom in the system. And then we basically use these curves as the, oops, I think I missed my last slide.
It's okay.
Yeah. So, no, but I mean, I wanted to thank my group and you for the attention, but I don't know why it's not here. I added it before, but let me see. long. Anyway, so this work was mostly done by my group at UNT, University of North Texas. So some of these people were responsible for some of these developments. Nevrite did all the simulations on the 2D materials. Edan did the refactoring in Python and did a lot of work on the code. I have some students right now in my group. Some of them are from the computer science. I think I've not updated it, but I'm always looking for more students or people interested in these projects, and I'm happy to discuss possible research projects. I'm sorry I was longer than expected. Thank you for the attention.